Imagine you are sitting inside a machine traveling faster than a rifle bullet. Not twice as fast, not 3 times as fast, 3 times the speed of sound. The air outside your cockpit is so thin that if you removed your pressure suit, your blood would literally begin to boil within seconds. You are at the edge of space, 78,800 feet above the Earth. The sky above you is not blue, it is black. You are so high that you can actually see the curvature of the Earth beneath you. And then, without warning, without a single alarm, without a moment to react, the aircraft around you simply ceases to exist. You are not ejected. You do not pull a handle. You do not make a decision. The machine disintegrates, and you are thrown into the void. This is not a movie. This is not a simulation. This happened. On January 25, 1966, a United States Air Force test pilot named Bill Weaver became the only human being in recorded history to survive the complete mid-air breakup of an SR-71 Blackbird at Mach 3 without ejecting, and lived to tell the story. 2 weeks later, he was back in the cockpit. Today, we are going inside that story. Every detail, every second. Every impossible survival factor that conspired to keep one man alive when everything around him said he should not be. This is the story of the most extraordinary aviation survival event in the history of human flight. And by the time we are done today, you will understand not just what happened, but how it happened, why it happened, and what it tells us about human beings, about machines, and about the absolute outer edge of what is possible. Let us go back to the beginning. To understand what happened to Bill Weaver on that January morning in 1966, you first have to understand what the SR-71 Blackbird was. Because the Blackbird was not simply an aircraft, it was a statement, a declaration by the United States of America that human engineering could achieve things that seemed to belong to science fiction. The SR-71 was the fastest air-breathing aircraft ever built by human hands. It still holds that record today, more than 60 years after it first flew. Nothing we have built since has surpassed it in operational service. Let that sink in for a moment. In 6 decades of aviation advancement, with all of our computers and composite materials and digital engineering, we have not built anything faster for operational use. The SR-71 was born from a program called the A-12 Oxcart, developed by Lockheed's legendary Skunk Works division under the direction of the brilliant designer Kelly Johnson. The Skunk Works was a place where rules did not apply, where engineers were given problems that were considered impossible and told to solve them anyway. And the problem Kelly Johnson was given in the late 1950s was this: build an aircraft that can fly so high and so fast that nothing on Earth can touch it. The Cold War was at its absolute peak. The Soviet Union had shot down a U-2 spy plane in 1960, capturing pilot Francis Gary Powers and creating one of the most embarrassing diplomatic incidents in American history. The United States needed a replacement, something that could not be caught. Something that could not be shot down. Something that would make every surface-to-air missile and every interceptor aircraft on the planet completely obsolete. Kelly Johnson delivered. The SR-71 cruised at altitudes above 80,000 feet. It flew at speeds exceeding Mach 3.2 in operational conditions. When a Soviet surface-to-air missile was fired at an SR-71, the standard defensive maneuver was simply to accelerate. The missile could not catch it. When Soviet interceptors were scrambled to chase an SR-71, the pilots would watch it disappear over the horizon before they even reached altitude. The aircraft was genuinely untouchable from an external threat, but the SR-71 had enemies that no missile could protect against. The enemies were physics itself. At Mach 3, the aerodynamic forces acting on an aircraft are almost incomprehensible to the average person. The heat generated by air friction at those speeds turns the leading edges of the aircraft to temperatures exceeding 500 degrees Fahrenheit. The entire airframe expands by several inches due to thermal stress. The fuel tanks, which were deliberately left slightly loose on the ground, sealed themselves through thermal expansion only after reaching operating temperatures. On the ground, the SR-71 actually leaked fuel. This was by design. The propulsion system was a marvel of engineering violence. The SR-71 used Pratt & Whitney J58 engines that were, in a very real sense, neither pure jet engines nor pure ramjet engines, but a hybrid of both. At low speeds, they operated like conventional turbojets. But as the aircraft accelerated past Mach 2.2, the inlet spike at the front of each engine nacelle would translate rearward, changing the geometry of the air intake, and the engine would begin transitioning into what was effectively a continuous bleed ramjet. The roar of those engines at full power was not just sound, it was a physical force. People on the ground miles away reported feeling it in their chests. And managing all of this, the thermal loads, the propulsion dynamics, the aerodynamic forces at the edge of atmosphere, required absolute precision. A small deviation in the angle of attack, a slight imbalance in the inlet geometry, a fuel system anomaly. Any one of these things could cause what was called an inlet unstart, a sudden, violent disruption of the airflow through the engine inlets that produced asymmetric thrust capable of inducing forces that exceeded the structural limits of the airframe. And that brings us back to January 25th. 1966, Bill Weaver was not a man who stumbled into history. He was one of the finest test pilots in the world. He had flown for the United States Navy before transitioning to Lockheed's test pilot program. He had accumulated thousands of flight hours across dozens of aircraft types. He was calm, methodical, technically brilliant, and possessed of the kind of ice-cold composure that defines the very best aviators. He was exactly the kind of man you wanted in the cockpit of the most advanced aircraft ever built. On that January morning, Weaver was accompanied by flight systems specialist Jim Zweyer, who occupied the rear cockpit of the SR-71. Zweyer was an experienced Lockheed engineer, not a pilot, but a man thoroughly familiar with the aircraft's systems. Their mission that day was a planned performance profile flight, one of dozens of test missions designed to push the aircraft's systems and gather data that would inform operational procedures. They took off from Edwards Air Force Base in California. The sky was clear, the conditions were good, everything was nominal as they climbed through the atmosphere, the J58 engines pushing them higher and faster, the altimeter unwinding toward operational altitude, the Mach meter climbing past 2, past 2.5, approaching 3. And then everything happened at once. The sequence of events that led to the disintegration of the aircraft began with a malfunction in the propulsion control system. At speeds around Mach 3.17 and an altitude of 78,800 feet, both engines experienced simultaneous inlet unstarts. This was catastrophic. An inlet unstart on one engine was dangerous and difficult to manage. An inlet unstart on both engines simultaneously was an almost unrecoverable emergency. The asymmetric thrust created by the unstarts generated aerodynamic forces that exceeded the aircraft's structural limitations instantaneously. The nose pitched up violently. The aircraft entered an uncontrolled departure from flight, and within fractions of a second, the aerodynamic forces acting on the airframe exceeded what the engineers who designed it had ever intended it to withstand. The aircraft broke apart. Now, here is where the physics becomes both the killer and the savior. At 78,800 feet, the atmosphere is extraordinarily thin, roughly 1/60th the density of air at sea level. In practical terms, when the aircraft disintegrated and Bill Weaver was ejected into the slipstream at Mach 3, the aerodynamic forces, while still enormous, were far less lethal than they would have been at lower altitude. At sea level, being thrown from an aircraft at Mach 3 would produce forces capable of tearing a human body apart. At 78,800 feet, the thinner air produced forces that were violent but survivable. Weaver was not ejected in the traditional sense. He did not pull a handle, he did not initiate the ejection sequence. The disintegration of the aircraft simply separated him from it. His seat belt, designed to withstand enormous forces, shredded. His pressure suit, the full pressure suit worn by SR-71 crews, more similar to a spacesuit than to conventional flight equipment, automatically inflated as cabin pressure was lost. And Weaver found himself in freefall at the edge of space. He was unconscious. He had to be. The forces during the breakup, the sudden decompression, the shock of the event, any or all of these things would have rendered him unconscious within seconds, if not instantly. And here is the thing about being unconscious at 78,800 feet in a full pressure suit. It may have saved his life, because Weaver did not panic. He could not panic. He was unconscious. His pressure suit maintained the atmospheric pressure equivalent of roughly 35,000 feet around his body. His helmet sealed. His suit protected him from the lethal cold of the stratosphere, where temperatures plunged to nearly 80 degrees below 0 Fahrenheit. His body, sealed inside that suit, was being kept alive by the engineering of the people who had designed his life support system. And as he fell unconscious, tumbling entirely without control, the thin air of the stratosphere gradually slowed his rate of descent. He passed through the atmosphere. The air grew denser. At some point, the exact moment is not recorded, and Weaver himself could not later say precisely when he regained consciousness. What he described in later accounts was a moment of profound disorientation. He was aware that he was falling. He was aware that he was alive. He could see the earth below him. He could feel the suit around his body. He had no memory of the breakup. The last thing he remembered was the aircraft entering its unusual motion, and then nothing. He was in freefall, and the parachute system built into his pressure suit, a system that activated automatically based on altitude, deployed. He landed in a field near Tucumcari, New Mexico. Jim Zweier, his crewmate in the rear cockpit, was not so fortunate. Zweier did not survive. The exact circumstances of his death were never fully established, but it is believed that the forces during the breakup, or the subsequent decompression, proved fatal. He was found near the wreckage of the aircraft. The loss of Jim Zweier was a tragedy that Weaver carried with him for the rest of his life, the knowledge that he had walked away from something his crewmate had not. But we must understand what Weaver's survival meant, because it was not simply a matter of luck. It was a convergence of factors so precise, so specific, so unlikely in their combination that the scientific and aviation communities have spent decades analyzing them. Factor 1 was the altitude, 78,800 feet. If the breakup had occurred at lower altitude in denser air, the aerodynamic forces acting on Weaver's body during separation from the aircraft would almost certainly have been lethal. The thin air of the stratosphere was, paradoxically, a lifesaver. Every 1,000 feet lower would have increased the aerodynamic loading. At 50,000 feet, the outcome would very likely have been different. Factor 2 was the pressure suit. The full pressure suit worn by SR-71 crews was not an afterthought. It was a critical life support system. Designed by the David Clark Company, these suits were the product of decades of development going back to the early days of high-altitude aviation. When cabin pressure was lost, the suit automatically inflated, providing the wearer with enough atmospheric pressure to survive. Without it, the sudden decompression at 78,800 feet would have been immediately fatal. The suit also provided thermal protection against the extreme cold of the stratosphere and structural support that may have protected Weaver's body during the violence of the breakup. Factor 3 was the automatic parachute deployment system. Weaver was unconscious. He could not pull a ripcord. He could not make decisions. The parachute system built into his suit was designed precisely for this scenario. It would activate automatically at a predetermined altitude, regardless of the condition of the wearer. That system worked exactly as designed. Factor 4 was the physiological response to unconsciousness itself. This is the counterintuitive one. A conscious person in the same situation would have experienced terror. Would have been fighting the fall, potentially making movements that could have compromised the pressure suit integrity or the parachute deployment. An unconscious body going limp offered no resistance, created no complications. The systems designed to save him could do their jobs without interference. And Factor 5 was the simple geometry of fate. The breakup occurred over terrain that, while not ideal for a parachute landing, was survivable. New Mexico's high desert, open land, no trees. No mountains directly beneath him. no water. He came down on land he could land on now after Weaver was recovered, after the medical teams arrived, after the initial shock was processed. The immediate question was, what had caused the accident? Their investigation was thorough. This was the United States Air Force test program. Every data point was examined. Every piece of telemetry that had been transmitted before the breakup was analyzed. And the conclusion, while not simple, was this. The simultaneous inlet unstarts, combined with a failure in the autopilot system that prevented the aircraft from dampening the resulting pitch-up maneuver quickly enough, had generated aerodynamic forces that exceeded the design envelope of the airframe. The aircraft had effectively been torn apart by its own aerodynamics. This was not a comfortable finding for the Lockheed engineers who had designed the aircraft or for the Air Force pilots who were flying it. The SR-71 was supposed to be invincible, and in a very real sense it was invincible to external threats, but it had demonstrated a vulnerability to the forces it generated itself. The response was immediate and comprehensive. The autopilot systems were modified. The inlet control logic was revised. Procedures for managing inlet unstarts were updated and practiced until they became automatic for every SR-71 crew. The aircraft continued to fly, and fly successfully, for another quarter-century. The lessons brought by the loss of Jim Zweyer and the near-death of Bill Weaver were written into the operational procedures that kept every subsequent SR-71 crew alive. But let us step back for a moment. Let us talk about who Bill Weaver was as a person, because his story does not end with his survival. In many ways, it begins there. Bill Weaver was born in Lansing, Michigan in 1928. He grew up in an era when aviation was still young, when the people who flew were considered a special class of human beings, daring, adventurous, possessed of a kind of controlled recklessness that separated them from ordinary men and women. He developed his love of flying early, drawn to aircraft with the kind of obsessive fascination that defines the people who go on to do extraordinary things in the air. He served in the United States Navy as a pilot, accumulating experience across multiple aircraft types and demonstrating the qualities that would eventually bring him to the attention of Lockheed's test pilot program. The transition from military service to test pilot work was a natural one for a man of his abilities. Test pilots occupied a unique position in the aviation world. They were both engineers and pilots, required to fly aircraft to their limits and beyond, to gather data that would make those aircraft safer and more capable, and to do so with a level of analytical detachment that was rare among aviators. At Lockheed, Weaver became one of the key figures in the SR-71 test program. He flew the aircraft extensively, accumulating deep experience with its systems and its behavior across the full range of its performance envelope. He was known for his calm professionalism, his technical rigor, and the absolute composure with which he approached even the most challenging test missions. He was, by any measure, one of the finest aviators of his generation, and after January 25, 1966, he was also something else. He was a man who had survived the unsurvivable, who had been thrown from a disintegrating aircraft at the edge of space, traveling at 3 times the speed of sound, and had lived to describe it, who had lost his crewmate and carried that loss, and who had still, 2 weeks after the accident, climbed back into the cockpit. That last detail bears examination. 2 weeks, 14 days after Bill Weaver was thrown from a disintegrating SR-71 at Mach 3, he was flying again. To most people that seems incredible. To some, it might seem reckless, but to understand it, you have to understand the psychology of test pilots and the specific psychology of Bill Weaver. Test pilots are not daredevils. They are not people who seek danger for the thrill of it. They are, in fact, among the most risk-averse aviators in the world, but their risk aversion is specific. They assess risk analytically. They understand what caused an accident. They understand what changes have been made to prevent it from recurring, and they make a logical determination about whether it is safe to fly again. They do not fly on emotion, they fly on analysis. For Weaver, the accident had a known cause. The investigation had been rapid and thorough. The modifications to the aircraft systems had been identified and were being implemented. The procedures had been updated. The risk that had caused the accident had been addressed. From Weaver's perspective, there was no rational reason not to fly. The irrational response would have been to let fear make the decision, and perhaps more than that, returning to the aircraft was, for Weaver, an act of respect. Respect for Jim Zweyer, respect for the engineers who had built the SR-71, respect for the program that he had given his career to. Walking away would have been the easier choice. It would have been the human choice, but Bill Weaver was not looking for the easy choice. He was looking for the right one. He climbed back into the cockpit 2 weeks later and flew. And he continued to fly for years afterward. Now, let us talk about the SR-71 program itself in the broader context, because Bill Weaver's story cannot be fully understood without understanding the world that produced him and the machine he flew. The SR-71 Blackbird entered operational service with the United States Air Force's 9th Strategic Reconnaissance Wing in 1966. Over the following 24 years of operational service, it flew reconnaissance missions over some of the most sensitive and contested airspace on the planet. It photographed military installations in North Korea and North Vietnam. It monitored Soviet naval movements. It gathered intelligence over the Middle East. It flew above conflicts and crises across the globe, its cameras and sensors collecting information that shaped the decisions of presidents and generals. In all those years of operational service, not a single SR-71 was ever shot down by an enemy. Over 4,000 missiles were fired at SR-71 aircraft during their operational careers. Not one found its mark. Every time an enemy attempted to intercept or destroy an SR-71, the aircraft simply outran them. The speed and altitude that made it so dangerous to fly were precisely the qualities that made it invincible to threats. The SR-71 fleet flew until 1989, when it was retired as a cost-cutting measure, a decision that many in the intelligence community considered a serious mistake. It was briefly reactivated in the 1990s, when it became clear that no satellite or UAV could match its specific combination of speed, altitude, and sensor capability. It was retired again in 1998, and this time the retirement was permanent. In its operational career, 32 SR-71s were built. 12 were lost to accidents. None were lost to enemy action. The accidents that claimed those 12 aircraft were the result of the same thing that had nearly killed Bill Weaver: the extraordinary demands that operating at Mach 3 at the edge of the atmosphere placed on both man and machine. Every one of those accidents was a lesson, and every lesson was learned. The people who flew the SR-71 were a very specific kind of human being. The selection process was rigorous beyond description. You had to be an exceptional pilot. That was simply the baseline entry requirement. Beyond that, you had to demonstrate the psychological stability to remain functional under conditions of extreme stress and disorientation. You had to possess the technical understanding to manage a propulsion and navigation system of extraordinary complexity. And you had to be willing to accept a level of risk that most human beings, when confronted with it in its full reality, would find unacceptable. The community of SR-71 pilots was small. Over the aircraft's operational career, fewer than 100 pilots flew it. They formed a brotherhood defined by shared experience of a kind that no outsider could fully understand. They had all sat in that cockpit at 80,000 feet, watching the sky turn black, feeling the aircraft shudder as the engines pushed toward their limits. They had all experienced the loneliness and the privilege of that altitude, that speed, that view. And they had all understood with absolute clarity that what they were doing was at the absolute outer edge of what human beings and their machines could achieve. Bill Weaver stood apart even in that company. Because he had experienced something none of the others had. He had been outside the aircraft. He had been in the void at those speeds at that altitude without the machine around him. He had experienced in the most direct possible way exactly what the SR-71 program was asking its pilots to risk, and he had come back. There is something deeply important in that, in the way the aviation community and the broader world has processed the story of Bill Weaver. Because survival stories have a particular power in human culture. They affirm something we all want to believe, that the human spirit, the human body, the human will to live, can overcome even the most impossible circumstances. That there is something in us that persists when everything around us has failed. But Bill Weaver's survival was not purely a matter of spirit. It was a matter of engineering, the pressure suit that kept him alive. The automatic parachute system that deployed when he could not. The altitude that reduced the aerodynamic forces just enough to be survivable. The investigation and modifications that came afterward. All of these things were the product of human ingenuity, of careful thinking, of engineering discipline applied to the problem of keeping human beings alive in environments that would otherwise kill them instantly. This is the deeper lesson of Bill Weaver's story. Not just that a remarkable man survived a remarkable accident, but that survival at the extreme edge of human capability is always a collaboration between the individual and the technology, between the pilot and the engineers, between the man in the cockpit and the men and women on the ground who built the suit, designed the parachute, analyzed the data, and made the changes that prevented the next accident. The SR-71 program was, at its core, a collaboration of that kind. A sustained, disciplined effort to extend the boundaries of what was possible. And the price of that extension was paid in accidents, in close calls, in the loss of men like Jim Zweyer, and in the harrowing survival of men like Bill Weaver. Let us take a moment to appreciate what was actually happening physically when that aircraft broke apart, because the physics of it are extraordinary. At Mach 3, an aircraft is traveling at approximately 2,200 miles per hour. In 1 second, it covers roughly 3,200 feet, more than half a mile. The kinetic energy of an aircraft traveling at those speeds is almost incomprehensible. When the SR-71's nose pitched up violently due to the inlet unstarts, the aircraft was subjected to aerodynamic forces that could be measured in multiples of the force of gravity, what pilots call G-forces. The structural limits of the SR-71 airframe, while extraordinary by any normal standard, were exceeded within fractions of a second. The titanium structure of the aircraft, and it was primarily titanium because aluminum would have melted at Mach 3 temperatures, simply could not withstand the forces being applied to it. The airframe failed, not gradually, not progressively, instantaneously. The aircraft that had been intact one moment was fragments the next. Weaver was subjected to those same forces for the fraction of a second it took for the aircraft to disintegrate around him. The forces were enormous enough to shred his seat belt, but the duration was mercifully brief. And then he was in the thin air of the stratosphere, and the forces acting on him were reduced to manageable levels. The thermal environment was equally extreme. At Mach 3, aerodynamic heating raises the surface temperature of the aircraft to hundreds of degrees. But Weaver, inside his pressure suit, was somewhat insulated from that. The suit provided a layer of protection, and once separated from the aircraft, the aerodynamic heating on his body was dramatically less than what the aircraft itself had been experiencing, because his body was no longer generating the same aerodynamic profile as the aircraft. The cold was the next threat. At 78,800 feet, the ambient temperature is approximately -56 degrees Celsius, nearly -70 degrees Fahrenheit. Without the pressure suit's thermal protection, Weaver would have been killed by the cold within minutes. With it, he was protected, and the pressure. At 78,800 feet, the atmospheric pressure is roughly 1/60 of sea level pressure, without the pressure suit. The low pressure would have caused immediate unconsciousness and death within seconds. The blood literally begins to boil in the absence of atmospheric pressure to keep it in liquid form. The suit maintained a pressurized environment around Weaver's body equivalent to conditions at around 35,000 feet, still low, still requiring oxygen, but survivable for a limited period with the right equipment. All of this happened simultaneously. And all of it was managed, not by Weaver, who was unconscious, but by the engineering built into his pressure suit. There is a profound irony in the fact that the very aircraft that nearly killed Bill Weaver was also, in an indirect sense, what saved him. The SR-71 program demanded pressure suits of extraordinary quality. The program's resources, its technical expertise, its absolute commitment to keeping its crews alive in an environment that was inherently lethal, had produced a life support system capable of preserving a human being who was thrown from a disintegrating aircraft at Mach 3 at the edge of space. Without the SR-71 program, without the investment it demanded in crew survival systems, Weaver's suit might not have been up to the task. Now let us consider the broader story of aviation survival in the test pilot era, because Bill Weaver's experience, while unique, did not occur in isolation. It was part of a larger pattern of pushing the envelope, and sometimes having the envelope push back. The 1950s and 1960s were the golden age of test flying, and they were also the deadliest years in the history of aviation development. At Edwards Air Force Base alone, where Weaver's accident originated, dozens of test pilots were killed during this period. The aircraft being tested were at the absolute frontier of possibility. The knowledge needed to fly them safely was being accumulated in real time, often through accidents, often at fatal cost. The men who flew these aircraft understood this. They were not ignorant of the risk. They read the accident reports. They attended the funerals. They knew that the statistical odds of a long career in test flying without a serious accident were not favorable. And they flew anyway, because they believed in what they were doing. Because they understood that someone had to push those limits, gather that data, take those risks, so that the aircraft that came after would be safer and more capable. In this sense, the test pilot community of the 1950s and 1960s was engaged in a collective act of sacrifice. Not sacrifice in the dramatic sense, not men throwing themselves into danger carelessly, but sacrifice in the disciplined, calculated sense of accepting known risk in service of something larger than themselves. They were buying knowledge with risk, and the knowledge they bought has kept countless other aviators alive in the decades since. Bill Weaver was part of that tradition. His accident contributed to the knowledge base of the SR-71 program. The modifications made as a result of the January 1966 incident made every subsequent SR-71 flight safer. The data gathered from his survival, from the analysis of how his pressure suit performed, how the parachute system deployed, what the human body can endure in those conditions, contributed to the development of crew survival systems that have saved lives far beyond the SR-71 program. This is how progress happens in aviation. Not through bold strokes of genius alone, though those matter too, but through the painstaking accumulation of hard lessons, paid for at enormous cost, translated into incremental improvements that gradually make the impossible routine. Let us also spend some time on the machine itself, because the SR-71 Blackbird deserves deeper examination than it typically receives in popular accounts of this story. Kelly Johnson's design philosophy for the SR-71 was built around what he called the KISS principle. Keep it simple, stupid. The aircraft was designed to be as simple as possible, consistent with achieving its mission requirements. This might seem paradoxical for an aircraft of such extraordinary complexity, but Johnson's genius was in knowing which complexities were necessary and which could be eliminated. The SR-71's titanium structure was a case in point. At Mach 3, aluminum was simply not an option. It would have softened and lost structural integrity at the skin temperatures generated by aerodynamic heating. Titanium was the only practical alternative. But titanium was, in 1960, an extraordinarily difficult material to work with. The machining tools of the era were not designed for it. The welding techniques were not developed for it. Lockheed had to essentially invent the manufacturing processes needed to build an aircraft from titanium. And the irony is that some of their early attempts were sabotaged by the titanium itself. Early SR-71 airframes showed unexpected corrosion, which was eventually traced to the fact that the cleaning solvents being used on the titanium had been mixed with tap water from a local water treatment facility. The chlorine in the tap water was reacting with the titanium. The solution was to use distilled water. An entire industry had to adapt its practices to the demands of this one aircraft. The fuel system was equally extraordinary. The JP-7 fuel used by the SR-71 was specially developed for the aircraft. It had an extraordinarily high flash point. It was so stable that it was notoriously difficult to ignite, which was a feature rather than a bug at Mach 3, where the risk of accidental ignition was very real. The J-58 engines used a specially developed ignition system called trethylborane (TEB) to start the engines and relight them in flight. Each engine carried a limited supply of TEB, and pilots managed it carefully. The inlet geometry was perhaps the most sophisticated aspect of the propulsion system. The movable spikes at the front of each engine nacelle had to be positioned with extraordinary precision to optimize the shock wave pattern entering the engines at any given speed. The difference between perfect positioning and slightly wrong positioning could be the difference between smooth operation and an inlet unstart. Managing this at Mach 3 required an automatic control system of considerable sophistication, sophisticated for its era at least, though it would seem primitive by modern standards. The aircraft also had to be fueled in a unique way, because it leaked fuel on the ground intentionally because the thermal expansion during flight would seal the tanks. It took off with partial fuel loads and was immediately aerial refueled by a tanker aircraft. Pilots would rendezvous with the tanker, take on a full fuel load while still subsonic, and then accelerate to operational speed. This was an extraordinary piece of operational choreography, made routine by the professionalism of the crews involved. The SR-71's cameras and sensors were equally remarkable. The aircraft carried a variety of reconnaissance systems, optical cameras capable of photographing a license plate from 70,000 feet, radar systems that could map terrain through cloud cover, signals intelligence equipment that could intercept electronic emissions from hundreds of miles away. On a single mission, an SR-71 could photograph 100,000 square miles of the Earth's surface. No other platform before or since has matched that capability in operational service. All of this technology existed in service of a single purpose, seeing what the enemy was doing without the enemy being able to stop you. And for a quarter century, the SR-71 fulfilled that purpose without a single loss to enemy action. The aircraft was, by any measure, one of the greatest achievements in the history of aerospace engineering. Bill Weaver was part of that history, not just as a victim of its risks, but as one of its architects. His test flights and the flights of his colleagues at Lockheed translated engineering concepts into operational reality. They were the ones who flew the aircraft to its limits, discovered what those limits actually were as opposed to what they theoretically should be, and contributed the data that allowed the aircraft to eventually be trusted with operational missions over hostile territory. The community of test pilots that shaped the SR-71 program was a remarkable group. Beyond Weaver, there was Art Peterson, who survived an inlet unstart that sent him into an uncontrolled maneuver that took him from operational altitude to 20,000 feet before he recovered. There was Bob Gilliland, the Lockheed test pilot who made the first flight of the SR-71 on December 22, 1964, a flight that must have required extraordinary courage, given that the aircraft had never been flown before, and the theoretical predictions about its behavior were just that, theoretical. There was Jim Eastham, whose deep knowledge of the aircraft's handling characteristics contributed enormously to the development of its operational flight manual. There was Mile Vojvodich, who flew some of the earliest operational missions and helped define what the aircraft could actually do in the field as opposed to in test conditions. And there were dozens of others, Lockheed test pilots and Air Force crews, who contributed their skill, their courage, and in some cases their lives to the development of this extraordinary machine. They were all part of the same story. The story of what human beings can achieve when they commit fully, with intelligence and discipline and courage, to pushing the boundaries of the possible. Now, what happened to Bill Weaver after January 25th, 1966, he returned to flying, as we have discussed. He continued his work with Lockheed, contributing to the ongoing development and testing of the SR-71 and related programs. He flew for years after the accident, accumulating further experience and further data. He retired from test flying with a career that, even setting aside the events of that January morning, would have been remarkable. In later years, Weaver became one of the key historical voices of the SR-71 program. He gave interviews. He attended airshow events. He contributed to historical accounts of the aircraft and its development. He talked about the accident with the measured analytical clarity that characterized everything he did, not dramatizing it, not minimizing it, but describing it with the precision of a man who had spent his career converting experience into understanding. He was clear about his feelings regarding Jim Sawyer. The loss of his crewmate was not something he moved past or put behind him. It was something he carried. That is what it means to survive when your crewmate does not. You carry it. You honor it, you make the survival mean something by continuing to contribute, by sharing the knowledge, by ensuring that what happened on that day is remembered and learned from. Weaver's descriptions of the accident itself are remarkable for what they reveal about human memory and consciousness under extreme stress. He remembered the onset of the unusual motion. He had no memory of the breakup itself. He regained consciousness to find himself in freefall, with no clear sense of how much time had passed or exactly how far he had fallen. His memories of the descent and landing are clearer, the operation of the parachute, the approach to the ground, the landing. These gaps in memory are consistent with what we know about unconsciousness and extreme physiological stress. The brain protects itself by not recording events that occur when it has been functionally shut down by the forces acting on it. In a sense, Weaver's unconsciousness was merciful in this regard. He was spared the direct experience of the worst of it. The story of Bill Weaver is also, importantly, a story about trust. Trust in technology. Trust in the people who designed and built that technology. When Weaver put on his pressure suit before that January flight, he was placing absolute trust in the engineers who had designed it, the technicians who had built it, the quality control processes that had ensured it would function correctly in the worst possible circumstances. That trust was justified. The suit performed exactly as designed. This kind of trust in technology, in the people behind technology, is fundamental to high-risk aviation. Test pilots cannot function if they do not trust the aircraft they are flying and the systems that are supposed to protect them. And that trust is not blind faith. It is informed trust, based on understanding exactly how the systems work and why they can be relied upon. Weaver trusted his pressure suit because he knew exactly what it was designed to do. He had studied it. He had trained with it. He understood its capabilities and its limitations. When it saved his life, it was not a surprise to him. It was the system doing exactly what the system was designed to do. This is a profound lesson for our era, when the relationship between human beings and technology is increasingly central to everything we do. Technology is not magic. It does not work through faith. It works through engineering, through testing, through the accumulated knowledge of everyone who has ever tried to solve the problems it was designed to solve. And the people who rely on it most directly, the pilots, the astronauts, the test engineers, are also, typically, the people who understand it most deeply. Bill Weaver's story is a reminder of that. A reminder that at the edge of the possible, where the margin between survival and death is measured in engineering tolerances and material properties and atmospheric pressure ratios, the difference between living and dying is often found not in the drama of the moment, but in the careful, patient, painstaking work that preceded it by months and years and decades. As we approach the conclusion of today's story, let us think about what the SR-71 Blackbird and the people who flew it represent in the larger context of human achievement. The 20th century was, among other things, the century of flight. In 100 years, human beings went from the first tentative hop at Kitty Hawk to regular commercial air travel, to supersonic flight, to orbiting the Earth, to walking on the Moon, to launching probes that are now traveling through interstellar space. The rate of progress was staggering, and every step of that progress was paid for in the same coin: risk, sacrifice, knowledge, and more risk. The SR-71 was near the peak of that progress as measured in raw performance terms. Nothing before it had been faster. Nothing since has been faster in operational service. It represented a kind of pinnacle, a demonstration that the combination of human ingenuity, industrial capability, and individual courage could produce something genuinely at the outer edge of what physics permits. And Bill Weaver stands at the heart of that story. Not because he was the most famous SR-71 pilot, or the most decorated, or the one who flew the most missions. He stands at the heart of it because his experience distilled everything that the SR-71 program was about into a single, extraordinary moment. The speed, the altitude, the risk, the failure, the survival, the return to flying. All of it compressed into 14 days in January 1966. When we ask what makes a person extraordinary, we often focus on talent, on ability, on the innate qualities that separate the exceptional from the ordinary. And those things matter. Bill Weaver's exceptional skill as a pilot was undeniably a factor in his career, and possibly in his survival. But what the story of January 25th, 1966 tells us is that exceptional outcomes are rarely the product of individual genius alone. They are the product of systems, of the collaboration between individual excellence and institutional support, between personal courage and engineered protection, between the man in the cockpit and the thousands of people who designed, built, tested, and maintained every system that kept him alive. Bill Weaver survived because he was an extraordinary pilot. He survived because he wore an extraordinary pressure suit. He survived because an extraordinary parachute system deployed when he could not deploy it himself. He survived because extraordinary engineers had understood the atmosphere at 78,800 feet and designed systems that could function in it. And he survived because extraordinary luck placed him above survivable terrain on a clear day in New Mexico. Remove any one of those factors, and the outcome is different. This is the true lesson of Bill Weaver's story. Not that any one thing saved him, but that everything working together, functioning as designed, aligned in just the right way at just the right moment, gave a remarkable human being the chance to live another day, and to climb back into the cockpit 2 weeks later, and to continue contributing for years afterward to the extraordinary human enterprise of pushing the boundaries of what is possible. Bill Weaver passed away on July 2nd, 2020, at the age of 91. He had lived a full, remarkable life, a life defined by courage and technical excellence, and the quiet dignity of a man who had done extraordinary things and never felt the need to make too much of it. He had survived the unsurvivable. He had lost a crewmate and honored that loss by continuing to fly and contribute. He had been part of one of the greatest aviation programs in human history, and he had told his story clearly and honestly so that others could learn from it. The SR-71 Blackbird, his aircraft, stands in museums now. At the National Air and Space Museum, at the Air Force Museum at Wright-Patterson, at museums and air bases around the country. And every person who stands in front of one of those sleek black aircraft and tries to comprehend what it was capable of, tries to imagine what it felt like to sit in that cockpit at 80,000 feet at Mach 3 with the sky black above you and the curve of the earth below, is standing in the shadow of Bill Weaver and Jim Zweyer and all the others who made it possible. What they did was not just flying. It was not just testing. It was the creation of knowledge at the absolute edge of human capability. It was the expansion of what we know and what we can do, purchased at the highest possible price by the best possible people in service of something they believed in absolutely. And on January 25, 1966, for about 12 minutes of freefall over the New Mexico desert, one of those people experienced the absolute limit of that edge, was thrown beyond it in fact, and came back. That is the story of Bill Weaver. That is the story of the SR-71 Blackbird. And that is the story of what human beings at their very best can achieve and endure and survive. The next time you look up at an aircraft passing overhead, know that somewhere in its design, in its safety systems, in the procedures that govern how it is flown, there is a piece of knowledge that was bought by someone like Bill Weaver. Someone who flew to the edge and sometimes went beyond it. Someone who paid a price so that you and the pilots above you could go a little further, a little safer, a little more confidently into that endless sky. We owe them more than we can ever fully repay. The least we can do is remember their stories. And here is the question I want to leave with you today, the question that I believe gets to the very heart of what we have explored in this story. If you were Bill Weaver, if you had survived the unsurvivable, if you had been thrown from a disintegrating aircraft at the edge of space and somehow lived, do you think you would have climbed back into that cockpit 2 weeks later? And what does your answer tell you about yourself, about courage, and about the kind of people the world has needed and still needs to push the boundaries of what is possible? Leave your answer in the comments below. Tell me what you would have done. Tell me what you think drives someone like Bill Weaver. And if this story moved you, if it gave you something to think about, something to feel, some new understanding of what human beings are capable of, then hit that subscribe button, because this channel is built for exactly that. For the stories that go beyond the headlines, for the history that lives in the details, for the men and women who shaped our world in ways we are still discovering. This has been the story of Bill Weaver, the Navy test pilot who survived his SR-71 disintegrating around him at Mach 3 and was flying again 2 weeks later.